Okay, wait for a while. Starting my lab. Okay. All right. Let us continue on our last lectures about filterings. All right. We have gone through, there are basically three types of filterings. All right. Yeah. And then a way to calculate them based on the ripple factors. And the most popular types of filtering is the what we call the capacitor types. Okay, simply because it is cheaper and then easily available compared to the inductor. All right, and then it basically solves most of the ripple factor problem, except for those high power application. So for LV side, basically there's no big issue at all, I would say. And then we move on. Okay, we go through the calculations. Okay, how to determine the ripple factors. So basically, all right, if you are experienced enough, right, you know, the higher the value, the better it is lah. Okay, so we now move. Okay, this is one of the classic examples I have shown last week. Okay, what happened is that if we put a capacitor, of course, you will be able to smooth up the output DC. However, it will create another problem which will give you a what we call a non-linear currents. That means the voltage and the current are not drawn in the same way. Okay, so you can see in terms of the waveform. So it happens especially when this what we call this when you place this capacitor there. Okay, when you place this capacitor. So similarly, okay, now we are measuring on the DC side. Okay, I made this one here, which I measure on the AC side. Okay, so still the same. Of course, that this is the AC side. We just move this one. You will still see that, you know, it will have a very sharp current surging. Okay, simply because the capacitor is start to charge, right? When the capacitor is charging, it is basically just like short circuit or with a very low resistance, and because of that, it will draw a lot of current at once, and then slowly you can see this is a characteristic, okay, of the capacitor, and these are the current that the grid side, the AC side, will see. Okay, so it causes basically two problems. We're talking about high power right now. Okay, two problems. One is obviously the harmonic is very high. Okay, most likely going to be around 100%. I'm not sure until you do the measurement. Okay, on the harmonics currents. Okay, and then secondly, harmonic are somehow, okay, direct or indirectly related to power factor. Okay, so because it's a sine wave, right, for the input, so they no longer have the same in-phase current and voltage. So because of that, okay, it will also introduce this power factor. Like I said, why it doesn't happen at LV, like your house, right? We have so many, because it's so small, so insignificant, okay? So it doesn't really matter, but if you use it at the high power applications, this is something that you need to really look into, okay? So yeah, so it happened on both AC and DC side. Okay, DC doesn't really matter because your load, right? But the most important one is actually the AC. Okay, AC is the grid side, right? TMD, like they have rule and regulation. If everybody going to introduce harmonic, right, then it's going to cause problem in their substation. Okay, subsequently it will cause a lot of nuisance tripping, overheating of the substation a transformer. So we can actually see that, okay, let's say we remove this one. So let's see what's the value first. 126, okay, this after calculate. Okay, of course, you will see that when we remove the capacitor, the voltage will go low, okay, because there's no smoothing. But now you see the current, right? A sine wave, right? On the AC side. There is no harmonic, I would say. I mean, even got by looking at the waveform, right, most likely it's going to be, less than 5%. Okay. So yeah, and of course the DC side, because of no filter, no capacitor, you do not have harmonic. So in fact, there are lots of harmonic. It's just because of this AC DC converter that is actually causing it. Okay, without you all noticing that it's actually a capacitor at your power supply, your side that is actually causing the problem. Of course, like I said, even small, like your charger, right? Basically, there's a AC, DC, and they're called flybacks. So it doesn't really cause a lot of problem. That is subjected to, like, every house, maybe you have 4 or 5. Okay, that is still okay. Because 4 or 5, okay, if let's say about 5, you got 30 watts charger, or even 100 watt, the most is only 500 watt. Compared to our PE substations of 1 MVA. So it's very, very small percentage. So it's not an issue. But of course, if you try to put like 1,000 of this, then it may start to cause problem now. Okay. So yeah, it's important, especially in the future, if you are working as a consultant for designing especially the condo. Okay, your condo with a few hundred units. Okay, nowadays easily you get few hundred units, right? So you have to take into account if every one of the houses at least have 1 or 2 chargers charging at the same time. Okay, then you have to think about how to, I mean the potential problem. The moment you build, of course, no load, it will say, oh, everything beautiful, jante. Okay, no issue. Okay, so this is one of the very good classical examples of non-linear load. Okay, non-linear load. So you can actually play around with it, or maybe we can try to do a bit of measurement of the THT. Okay, wait, let's THT. Okay, we have a block, okay, to measure THT. In fact, we got 2 different blocks of doing that. Okay, okay, in this case, we will try to use the, okay, here. Yeah, we got 2 different blocks. Okay, maybe we just put here. Okay, then. Okay, this one, the output is not in percentage, so I think we need to multiply by 100 later. Oh, okay. Not sure if 50 or 60. If this one I follow textbook, is 60 Hertz. Yeah. Yeah, so it's very, very low. Okay, so even you time 100, right, is less than 1% of THD. Okay, because it's almost sine wave. But like I said, if we do introduce a capacitor or different capacitor value, okay, just now I think it's 126, right? Okay. Okay. So you can see that yeah, after we just add the capacitor, immediately, right, the THD will become, time 100, is 185% of THD. You just add one. So you see, you are solving the ripple problem, we are creating another problem, right, at the end. So as an engineer, you have to be aware of that, okay, and yeah, work out the solution. It's just like, any medicine, right, you eat, right, you solve some of your illness, but it does give you some side effects. So you have to, yeah, work it out, which one is much more important, all right, or how to, solve this. So I hope this will give you a very clear idea about the advantages and disadvantages of using a filter, because in a lot of the electronic textbook, they only teach, this rectifier, which is AC/DC, and filter. That's all. End of story already. They don't talk much about the problem. But in power electronic, I would like to stress this because if you go to the industry, you see this problem, you have no idea that the filter that we study in our analog actually causing problem in the grid, especially in the power industry. Okay, so these are the knowledge gap, okay. I also don't know why not much of the textbook, even the textbook I introduced you all, not even care to talk about this. So I added this just for you all, not just about design the filter, but you have to know the problems. Okay. All right. Now, at this point, any questions? Hello? Okay. All right. So now let's move on. Okay. So remember, capacitor, because of their charge-discharge nature, they will cause non-linear, okay, what we call a load, okay. So okay. Similarly for, okay, inductive is much more better, okay. It doesn't really cause, because the charge-discharge characteristic is very much different. Three-phase LC, okay, as long as you have a capacitor there, even you combine both, okay, like we will still have the what we call the non-linear problem. Okay, so now how do we going to solve it? Okay, so there are few solutions, okay. Yeah, come back to this one, the filter thing. Now, in the old days, right, it's not a problem, right? I mean, AC to DC we charge because most of the application are low power. Remember, I say low power again. But I believe in the near future, this is going to be a big problem. At least I think not long away, I will foresee that it's going to be like maybe in the next 10 years, it's going to be a big problem. Why? Okay. Now, if we look at the trend of our EV, electrical vehicle now, okay, so if in the future, most people start to own electric vehicle, so what they do when they drive home, it's just like you will treat your EV like your handphone, right? The moment you park back in your car, you just charge it, right? Make sure that tomorrow morning your battery is 100% so that you can drive. So be it in the terrace house, be it in condo, every parking have a AC to DC. Remember, your EV is battery. it's definitely going to be AC to DC converter, and there is no longer a low power. Okay, imagine your R here is your battery, and everyone go home and charge. Then I believe the harmonic and the power factor will be nightmare for sure. There is a reason why even now we will see some of the so-called charging point at certain petrol station, at some shopping mall, right? You look at it, how many? Less than 10. Why? Simple lah. If you got 10 car parked in there, you charge at the same time, you know, the PE transformer will have problem because harmonic. So they calculated max is like that. But it's no issue, like I said, simply because the owner of the EV are still very less, not significant. You know, like I say, like it can be 10 or 20 years. By the time you already become senior engineer, okay, if you work out there as consultant or whatever, so, all right, then, you know, you should be able to, you know, provide a good solutions. And oh, I studied this in power, you know, it's just because of this problem, blah, blah, blah. Okay. So yeah, sometimes you will notice that the knowledge you learned 10 years back, right, it actually can help you, you know, in the future to solve certain problems. Just because we don't, it's our education system. I won't blame you guys. It's our education system is too much on exam oriented in the way that everybody just focus on the question, answer, and then get their marks, and then that's all. Okay, the knowledge part is actually put aside. Okay. Okay, so now, how do we actually solve this problem? Okay, we already have solution. Okay, one of them, okay, we call it power factor correction rectifier. Okay, now the rectifier AC/DC, what we see so far is just a normal one, but now we can use feedback control to do that. Okay, now this is the power factor corrector. Okay, controlled by the PWM. Okay, and then Irec is the rectified current, which is the DC side of the current, like I showed you just now. It will feed back, okay, to the PI. And then it will also have the rectified voltage, okay, and it will also feed back, okay, here. And of course, lastly, it will reference with your DC output, okay, AC to DC converter, DC output will feed back here, okay, and go to, there are two PI controller here. This is what we call a double loop control. Okay, now let's say I want to set, you know, 400 volt here, we set 400 watt, and your rectifier, okay, you will take your output lah, right, and try to set to 100 through the first PI controller here. Okay, through the first PI controller here. Okay, the first PI help you to set, okay, the output voltage. The second PI, this part, this whole part, okay, is to help to change. Okay, you see, it takes the reference of the current and the reference of the voltage. Try to match them together so that the output, this is the Vrec, okay, or voltage rectifier, and this is the Irec. So it actually takes the Vrec as reference, try to control that. Okay, you don't draw the current in this way. You have to draw the current exactly like the voltage. Okay, so this can be done by PI controller, okay, which is your control engineer. Okay, and this one we use double loop. Now most of the general feedback control is just a single loop. Okay, I've been showing so far. So if you want to control voltage magnitude and some other, you know, entities, then you need to combine double loop or triple loop. The most I see is double loop so far in power electronic. Of course, in other applications you may have more than that, but in the arena of power electronic, these are the method we use. Okay, then you will use PWM, okay, to control, okay, this power factor rectifier. That it will give you the what we call the sine wave. Okay, I mean, it will reduce the harmonic, improve the power factor. Okay, all right. So these are the equation. Okay, the VDC. Okay, the GI. All right, the error. Okay, the control equation. Now, in order to implement this, okay, this is how we're going to do. Okay, first of all, this one also not upload yet leh. Okay, never mind. Okay, we have an AC input. Okay, and then we measure both the voltage and current for your references. You will notice that, right? You will actually improve the power factors. Okay, up to 1. All right. And then we have a bridge rectifier. Instead of directly connect to a capacitor, what we did is that we add this part. We add this inductor. We add a diode. Okay, and we add a switching transistor here. Okay, we have switching transistor. So can anybody tell me what is this topology here? Hello? I already teach this one. Okay, because this AC to DC is a large chapter already. Can anyone tell me what is this whole part lah? Okay. This whole part. Because this is very important. Okay. Key information. Hello, hello, hello. You're still asleep. Don't worry, this is our last class already. Okay, please be awake. Hello, you guys there?
Oh, yes, sir. Okay.
Yes, what is this? Sorry?
Still thinking.
Still thinking, Wow. Give you a little bit of hint, it's under DC-DC converter. So far forgotten already, you guys. Wow. In fact, half of the class are not here, I know, even with C90 over student, right? Because at one time I didn't close the meeting until 10 o'clock. There are still 40 over students here. Anyway, okay. Still don't know. Yes, you are correct, Matthew. So you can see it's actually a boost converter. All right, we have an inductor, a diode, okay, and a switching transistor. So now, by combining these two, that means if you look at we have a AC to DC converter, AC to DC, and then we just combine it with another DC with DC. Okay, of course there are so many different topologies. Okay, the one that we are going to use is the boost converter. Remember I say the power electronic, right? You need to know all these components, the topologies. So it's just like a Lego part. You know, you take one part AC, DC, you combine with whatever part, right? You are creating, okay, a new types of converter that may be able to solve some problem. Now, in the old days, right, we really just learned 4 types of converter, AC, DC, all this. Okay, not much of combine back then. Okay, But of course, slowly you can see as the research move on, right? So when they have this problem, in the old day, they had no, they just have no solution. Now they say, oh, there's nothing we can do, right? You know, that you cannot control the capacitor. Then of course somebody will think, oh, no, we can do something on it. So it used the DC-DC converter knowledge, okay, that to combine them. Because this switching transistor, apart from doing the boost, right, it actually control how this capacitor charge and discharge. Right, when you short circuit, right, when you turn on your short circuit, right, you are discharging the capacitor. Okay, and then when you turn off, right, you are charging the capacitor. So by changing the PWM, okay, with certain frequency, you can control how the capacitor charge and discharge. Now, because of we don't have the control, that's why we have the non-linear output. We cannot control how, but with this one, okay, the PWM is, you know, by the feedback control here. Okay, so we can control how the capacitor charge and discharge. So we can actually make them sine wave, okay, at the output here and do the power factor correction. Just simply combine these two known things plus, okay, the double loop control. So this is how people, you know, work things out innovatively lah. I would say, okay, they work it out innovatively. All right. Another advantage is that, okay, you can boost your voltage. Now remember our AC single phase, the peak is only 325, right? The peak voltage, 325. Okay, what for peak, and of course 230 RMS. And our application, like for example, this is a very classic example that your EV battery easily you need 400 watt because most of the time they charge on 3-phase. But now your house or the condo you live is only single phase. Okay, then you only got 230, okay, where the peak is 325. How are you going to get 400 watt? The boost converter is a solution as well. So this boost converter serves multiple purposes. The first, to boost the voltage to the higher voltage than the one you get from the input. Okay, that is the basic operation of the boost converter. Okay, and secondly, it controls, okay, the capacitor charge discharge so that it will draw current in a linear way. Okay, so that your power factor and the harmonic can be reduced. Okay, so you can see that this is the Vrec. Okay, this is the Vrec. Okay, the green color is the VDC you want to set. Okay, and then the VDC is here, the output voltage. Okay, and of course the IL. Okay, or the I rectifier, the rectifier output current. Okay, so when we do this, you can see this demo here. Okay, all right. So I already run this one because it takes quite a long time to run. Okay, you can see that I set 400 watt output. This is my input, 325 only, the max. Okay, and I can achieve 400 watt output. And the thing is that we can see the output. Okay, so this is the filter output. Okay, the filter output of the rectifier. So you can see that, yeah, we still have some ripple. Of course, you can reduce it, okay, by calculating the ripple factor. And of course, much more complex compared to non-control. You have to deal with some of your PI control, okay. And of course, when you do switching, right, there will be switching frequency, okay, to deal with. Okay, I'm using 50 kilohertz of switching frequencies. And then you will see that now the most important is actually to see your harmonics. See, the one is your voltage, the below is your current. Beautiful, right? We no longer have this harmonic. Okay, I mean have lah, very low harmonic. Okay, compared to the one that I show you without any control. Okay, so our harmonic is very high. Now you can see the voltage draws sine wave, the current also draw in the sine wave manner. Okay, so this is how the what we call this power factor control rectifier, or in short we call it PFC lah. Okay, in PFC. All right. So like I said, so this is one of the solution. Okay, it's actually already implemented in most of our, this what we call the EV lah. Okay, the EV that we use. Okay, otherwise it's going to have a lot of problem. Even though with this one, right, we still have some limitation one. If you connect this to, let's say, 50 cars, you will start to see some problem. But this is to let you know that this is one of the solutions. Remember, if you one day you are tasked to say, oh, I want you to design a charger for EV, you don't simply design with a capacitor, sure won't get approved one because the harmonic is too high. So at least you have to know that, okay, we can do that, by, using AC DC converter, and then inductors. Okay, this is the the boost converter part lah. Okay, and the boost converter part, and then how we need to add this two set of PI control. Okay, to actually solve the problems. Okay, so at this point, any questions? So these are basically one of the solution. Okay, for high power AC to DC. Okay, another application of the high power AC to DC is the telco base station. Okay, telco base station, they actually running using DC because these base station, right, for DG, Maxis, okay, all these telco base station, okay, for them to transmit and receive our phone calls. Inside, all these equipment they use, okay, their router, okay, the RF, they are all running in DC. Okay, so they actually have a very big rectifier inside to power up all the equipment, okay, in every one of these base station. So base station are usually two, depend on where they put lah. Okay, they are actually very dense, they are very dense. Every part you can see rooftop. Okay, they are these base stations. Okay, so especially those big ones, you will see that they are small houses. Okay, maybe I'll show you. And they are actually taking a lot of power or energy simply because they require this. Okay, let's see. I try to type base station. So for those who are in the comm industry, okay, I mean, it's no surprise, one day you may work in comm industry because they require power people also. Okay, those power people to, okay, you will see that, where is it? Okay, something like that. Cellcom, DG, of course, this one is portable lah. Okay, this one is portable. You will see those base station, something like that. Okay, something here. All right, so inside here, they actually have the equipments all running in DC. Okay, they're all running in DC. They require a big rectifier, okay, to actually supply them, okay, for this. And then their coverage map, if you look at it, okay. Okay, coverage map. Okay, if you look at their coverage, man, it's quite dense actually. Okay. This is our Malaysia communication. So it's a very good reference. In fact, all the website, they have this map lah. Okay. So it will actually tell you, okay, now you see all the red color is all 4G lah. We have 4G. Still some of the places you can see here, right? They're still running at 2G. The green color at 3G. So it is actually very, very dense. Okay. When you zoom into maximum, you will see that there actually is a car. It's all the small circle dot. Let's say I zoom in here. Okay, for example, these are the road here. Okay, see along the highway or road, right? You can see these are the dot. So each of the dot represent one base station, and you can see along the way there are more than 10, right? So these are all, power, AC, DC converter required to power all the equipment, even though these are 3G, a bit of 4G here. That's why when we drive, right, sometimes say, how come no 3G? It's because of this, or if you have this, information, you will roughly know, especially when you want to travel to some places not so urban or rural places, it's advisable to look at this map here so that you will know that, which other place got. Of course, now if you go to KL, then of course it's the most dense place here lah. KL 100%, right? PJ, all this, and imagine each of the dot I'm talking about is one high power AC DC converter, and TMB had to supply all of them to make sure that they are working. Okay, so that we can have a communicate. Okay, it looks like very hard, but if you look at the whole country, right? In fact, our coverage is less than 50% or. See the whole Malaysia. Of course, all the big city we have full coverage lah. Along the coast side we have full coverage lah. Not full also some certain place. Okay, here this part also don't have. But okay, at least you can know. Okay, in the middle, Genting of course got lah. See our coverage, and you can see Sabah and Sarawak even less. Okay, so this is our coverage. This is also the reason why Elon Musk, Starlink, okay, is gaining the the market, because when you have Starlink, you do not no longer require to have this base station anymore. You can go in the middle of nowhere, you still can have internet up to near to 5G speed. Okay, for the Elon Musk Starlink thing lah. Another good business opportunity. Of course, Starlink draw the power from solar panel, outer space. So yeah. Yeah, that's the beauty of science and engineering, right? Okay, so enough of this topic thing. Come back, okay? So don't think that these things are not important. They are extremely important. Without this one, none of the base station will work. Okay. All right. Okay. Now we move on to the next one. Okay. Now we the power factor correction rectifier. Okay, or PFC rectifier, we control them at the DC side. We control the what we call power factor and harmonic at the DC side. Okay, so there is another way of this is just to show the controller. Okay, the waveform of all this. Okay, this is also the output. Sorry, just. Okay, yeah, the THD you can see is around 4, so less than 5. Okay, less than 5. Of course, initially you will have a spike, because as long as you have a control, PI control, okay, be single loop, double loop, right? Unless you tune it so well that it won't have overshoot. For me, I just simply tune the few value that can get my output, that's all. Okay. Okay, the next one is. Yeah, this one actually show all the details. This the scope here. The scope here. Oops. Okay, here scope show all the controls. Okay, the output. Okay, of the control. And then the output waveforms. Okay, on the AC side, AC DC side. Okay, these are just the THD in detail. Okay, normally we only look for the THD will do lah, unless you are the engineer who are going to design filters for the harmonic, then you may need to see the FFT lah, or else you don't. You just need to see the THD. That is good enough. Okay, like I said, application of this already have incorporated into the onboard charger of the EV. Okay, so when you can straight away connect your car to a single phase, because our car, right, actually have different options of charger. Okay, onboard charger means that it's built in. Okay, built in, which is on board lah. We will take the AC here. Okay, the AC from the wall or single phase. Okay, which is designed for your car to charge at your house or the parking lot. Okay, and the other way of course, this type of charging is called slow charger. You don't expect to charge your car up to 80% within 30 minutes. When you use this type of charger, it's usually like our old ways of charging, because the current you can draw from the outlet socket is limited. Okay, so this is more or less the 8-hour kind of slow charging. Okay, so it's usually designed for overnight when you go, especially you go home and charge, you go sleep, tomorrow morning you wake up and you go, you will get the full battery. And those at the parking lots also got two types. One is also the wall. The other one is the what we call Tesla charger, the one very big one. That is called fast charger. Okay, that type of charger is called fast charger because with that type, you can really charge your car up to 80% in less than 1 hour time. All right. Okay, so now we move on to the second way of solving this problem. Remember the one we showed just now, okay, is we control it at the DC side, okay? And another method is that we can control it at the AAC side, okay? So in this one we call it AFE, Active Front End Rectifier, okay? So control loop still the same, okay? We still need to use two what we call this two PI. Again, the first PI, the outer loop, the first PI to control the DC voltage you want. The second PI, okay, you are controlling the AC voltage drawing. That's why you need the PLL. You need the PLL, you need the I grid and the V grid. Okay, the only difference is, okay, you are controlling, okay, the AC current, how you want to draw it. Okay, the PFC is you are controlling the DC. So the whole structure is the same, okay, except the control part. Okay, so this one is V rectifier, so no need to have any PLL. But this one you control on the AC side, right? Then you need a PLL. Okay, you need a PLL, okay, to control. So by doing that, instead of using a rectifier, you are using a bridge, okay, the H bridge here. It's just like an inverter already, but it just works in another way around. So the inverter, this one you can see we are it's still an AC to DC converter, but we are using a H bridge. And then, like I said, the control is at the AC side, Okay, the DC side, nothing changed. I still put one capacitor, put a resistor, but I control it at AC. Now, previously is, okay, the AC side, no change, but I control an AC side. So the control part is at the DC side, okay, DC side. Okay, it's DC side. All right. All right, so how this control works, okay, like I said, these are the feedback, the DC, the VCC is here. These are the feedback. Okay, again, these are the control I showed just now. All right, we have the, you can control active power, reactive power, you control the power factors. Okay, similarly, okay, this one also will produce PWM. Okay, so this is the S PWM thing, huh? Remember when we have this DC to AC SPWM, okay? We are controlling with the SPWM. And then the inductor, okay, where we move the inductor, we actually move the inductor into the front here at the AC side. So we call it line reactor. Anything at the AC, we call reactor. Anything at the DC, we call inductor. Okay, it's the same thing, but we name differently. While listening to the name, we will know that where this thing is. If I take out, hey, can you put the reactor there? Then you saw reactor means AC, right? So it's AC side lah, like the one we study the thyristor switch control or switch capacitor thyristor, so control reactor. Okay, and then yeah, we measure the inverter current. Okay, and then okay, you see it's just like inverter, but it's not invert from DC to AC, but we switch them to rectify. Okay, from AC to DC. Okay, so sometimes you don't look at this, you say, oh, this one sure inverter. No, not necessary. Okay, that's why with a good proper control, you can make a bidirectional, what we call this inverter lah. Okay, you can rectify, you can invert. So we call bidirectional. All right. So okay, let's see. I think we are almost done already. Yeah. So once you run, right, again, you will see that you can actually draw the same voltage, okay, and current, okay, in the sinusoidal wave, okay, in the sinusoidal where you can improve the power factor as well as, you know, reducing the harmonics. Okay, so again, we can look at this 5.7. Still consider high lah for DMB. Okay, this is because I didn't tune it properly. All right, and you can see that in FFT it's much more cleaner. Okay, it's much more cleaner. All right. All right, I think we are done already. Okay, so yeah, let me see. I still have this thing or not. Yes, class. Rectifier. In fact, this type of advanced rectifier is not even mentioned in the textbook, you know. Yeah, you can look at the textbook, they don't even mention about active front end. Most textbooks nowadays is still very old school. Active, not this one. Okay. The same principle, right, can actually apply to both what we call this three-phase as well lah. Okay. Where is it? Control active front end. Okay, I don't know where I keep it. Okay. when I make all this, right, sometimes it's really, created a lot of folders just to make sure that it works. Active front end, I don't think I have kept this in my current folder, but anyway. Single phase, wait, I think I find. Oh, wow, so many files. In short, sometimes they call it active rectifier because the rectifier you are using the diode only, right? So you does not have any switching. Okay, when you does not have any switching, we will call it this rectifier. But now this rectifier, we have some form of switching. Okay, so when we have some form of switching, so we call it active rectifier. Okay, trying to locate my file. Okay, I think it's this one. Not sure. Let me just try it. Okay, not sure is it this one. I think so. Looks the same, right? Okay, these are the bridge already. So okay, let's try. So when you have a PI and all this, right? It will, yeah, it will take a while to run for just 1 second here. You will most probably study something like that in your master courses, okay, master in power electronics, because these are still, some of them is considered research based, okay. So most undergrad, they don't talk about this. But don't worry, this won't come out in your exam, okay. So they will say, wow, the active front end. Okay, I think, yeah, let's see. Okay, we open, yeah, this is the correct one. Then we can have a sine wave. Okay, sine wave input output. Okay, yeah, harmonic a bit high because you can see it's still not very sine wave. Okay, there is something to do with the control, something to do with the line reactor. Okay, switching frequency, so much more parameter you need to work on, okay, in order to get the desired output of 400 watts. Okay. Yeah, the filter is not that good in this case. You can see, like I said, I just don't tune it properly. Okay, but you see the ripple is very high. Okay, most likely the capacitor value is too low. I already put 3000. Okay, so that will give you the ideas of all this active front end. Okay, where this active front end is using. Now, active front end is currently okay, is actually used at the what we call this the Tesla DC charger. Okay, the Tesla DC charger. Those you plug on the wall one is called the AC charger, like the one I show you. Okay, Tesla DC charger is this thing is called DC fast charger, meaning that the moment the output of the plug is already DC. Okay, yeah, complete guy. This is a very good guy. Okay, so this one is AC charger. Okay, you have the onboard charger, right? And this one is the DC charger, meaning that straight away here already DC, go pump into your battery. There's no converter. The converter is built in here, that's why it's much more bigger. Okay, all this they call supercharger. Is basically the higher the power it is, right, the faster you charge. And those parking lot, when you see something like that, okay, and the output is DC, okay, so that is the what we call the DC fast charger, okay. So it bypasses the onboard, okay, charger, okay. Now you see if you're using onboard, okay, you use this one and you see it show you the difference, okay. So the onboard charger is basically a normal slow charger, okay, that you can install at your house. And the DC charger, and I'm talking about this part, okay. Now this part again, like I said, if like this one, if you have so many of these, right, you're going to have a harmonic problem for sure. Okay, so the normal rectifier thing won't work, okay, especially some of the country, they already have so much of this. Okay, Malaysia don't have yet. So one of the solution, like I said, okay, is this active front end. Okay, the active front end. So yeah, for developed country, okay, I'm not sure because I never worked there for any EV charger project. I believe this will be a future trend for many of our Malaysia market. Okay, so there are still many research going on how to further improve this one. Okay, so as far as I know, one of the one that very popular one, I will call it Vienna. Okay. Okay, there's a type of rectifier called Vienna rectifier. Okay. Okay, apply to three phases. Okay, apply to three phases. Still in the research, they already start to have application to all high power. So they will actually have three different switches here to actually control the charge discharge of the capacitor. Okay, control the charge discharge capacitor. Of course, we have a reactor at the front end. So this is another type of what we call this front end active rectifier. So this is one of the method. Okay, people are trying to improve. And Blacksim have this model. Okay, you can open. Okay, this is how they control it. So you can see Blacksim is also quite up to date. They have this what we call this Vienna rectifier. If I'm not mistaken, let's see. Blacksim. Yeah, let's see what we have. I think it's on. Okay, buck boost, flyback, inductor, chopper. I think it's under power supply. Diode rectifier with digital control. Dual active cyclo converter. Single phase active filter. Single phase active filters. Okay. Well, this is very different types. Okay, no, this is not the active front end. See, we have active front end or not. Oh, this one is the old type. Oh, Vienna. Yeah, they do have the Vienna type of what we call this rectifier, but they don't have active front end. They also don't have, oh, 3-level PFC, okay, power factor corrector, okay, this PFC. Okay. So they have a 3-level PFC, okay, you can see literally a boost converter part, okay, running at 100 kilohertz. And these are the controls. Some of the basic calculations, switching and so forth. The good thing is that they always have the references, okay, so you can always refer to the paper like, okay, this one is from which paper, okay, it's 1995, okay, then you can always refer to it. Okay, Vienna, okay, like Vienna, okay, is in 1994. You can think that like, wow, it's already almost 30 years, right? But it's still not fully commercialized like what we have nowadays, you know. So technology, when the first idea came out 30 years ago, it really took time to people slowly implement. Of course, it always started in simulation, started on a piece of paper and work on a small prototype on the PCB, and then slowly they need to publish paper, so that people look at the paper say, oh, this one, you know, are there potential for commercial? And when there are potential, there must be have some company willing to, like, for example, you know, provide you a research grant, say, okay, I want you to make this as a real product. You know, they will give you 3-year grants, so you can use the grant to make the thing, and all the whole process, right, easily takes up to 10 to 20 years, easily. Okay, so what we have today is not like what just happening last year. I mean, the handphone itself, it's not like, you know, 3G, 4G thing. It took a long way until what we can enjoy the technological advancement of what we have today. All right. Okay, so the rest of these I'll leave you to you all to have your self-exploration. Okay, to be honest, I do not know all of them. Okay, there's so many of them to learn. Okay, so all right, I think yeah, we have done okay for our power electronic classes. Okay, we covered the 4 converter, at least the minimum for the undergrad level of all of these 4 converter. Okay, I have fully covered. I even gave you some extra, something like that. Okay, but the minimum, rest assured, okay, you get what you need to know for an undergrad degree. All right. And then, yeah, we also talk about the transistor, the switching device. Okay, diode, MOSFET, IGBT, thyristor. Okay, these are the 4 types commonly used in the converter. And you will notice that for DC-DC converter, mostly they are MOSFET. For the any AC, AC or AC-DC is thyristor, mostly. Of course, we still have, like in this case, even for, you know, this is AC-DC, right? Well, we still use MOSFET. Okay. And again, like the PFC also, okay, we have diode and MOSFET, okay, for the switching. So it does not really limited to only DC-DC. So the trend, it seems like the transistor is now slowly going to eat up from DC to AC and DC to DC market, okay, into the AC to DC already. Slowly, you can see the popularity, okay, of using this diode. Okay, and then, all right, I think we are pretty much done here. Okay, any questions?
No, sir.
Okay, all right. So now a few things, okay, for the announcement for next week. For this next Monday, okay, we are going to have the assignment demo. Okay, so the demo is just to show me your group. Okay, either one of you attend is enough. Not 3 of you. Okay, you just need to show me your simulating model as well as the Plex model, and you have to show demo. Okay, it can run. That's all I need. no formal presentation required. Okay, so we will start at 9:30, okay, to 12:30. Because one group 5 minutes, we got 40 group, you know. So yeah, it's going to be around 2-3 hours. Okay, so first come, first serve. Please come early. I mean, if you have class, I mean, it won't take you that long. Okay, when your group come, you just, one of you just come here and then share your screen, show me your model. Okay, because remember your rubrics, right? It consists of MATLAB and Plex and the whole report. So because from the report, I cannot judge whether your Simulink or Plex is working or not. So the purpose of this is to prove it to me that yes, what you show me in your report is actually working or running. Okay, so that is the thing. Okay, now in order to save some time, I know that when you run thermal, right, it's going to be very long. So please, I just want to see your model that is going to run without thermal. Okay, so I mean for the live demo, okay, you just need to show me the one without thermal. If you want to show me the thermal, you have to pre-run it first. Okay, but for live demo, okay, please prepare the model that is that you can run normally. And then okay, what else? Okay, I will set a class schedule on Monday. Okay, 9:30 to 12:30. After 12:30, I will not entertain anymore. All right. So I assume that you didn't do your demo lah. Okay. And then okay, the report submission, right? Yeah, you can submit on that day if you want. Okay. And then the deadline I said is on Friday lah. Okay, next Friday. So yeah, you still have plenty of time to finish out a report, right? In the way that is presentable. And then okay, yeah, I think pretty much done. Okay, I said, okay, just one of you need to come and then let me know who are the team members so that I can, what we call this, can record them. Okay. And for final, okay, right, this time is going to be physical. Okay, this time is going to be physical, and I'm going to set the questions, 5 questions, right? So basically one question cover one chapter lah. So it's very straightforward mapping. Okay, so it's going to be like one question on the device, one question on DC-DC converter, one question going to be DC-AC converter, one question to be AC-AC converter, and one question to be the DC-AC converter. So each of them, so you can roughly gauge how to work on it. Okay, and then for those who midterm score below 10, you need to work a little bit harder lah. Okay, so that we still have the 50% ruling thing. Okay, so you need to, yeah, the 50% rules thing is there. If you don't score 50 marks over 100, okay, and I mean in the mark distribution, you need to score at least 25 marks, right, out of 50. Okay, in order to pass. So that is the minimum passing. All right, so 25 marks if you have your midterm is 10 marks, all right, or above lah. Many of you also achieve that. So you already got 35 marks, all right. So 35 marks meaning that your assignment, okay, you just need to achieve 50 marks in order to pass. Okay, so this is how the distributions it is lah. All right. Okay, if someone is talking, can someone also like, Yeah, the video is on, showing the whole class on your ceiling. Can you just kindly turn it off?
Sir.
Ah,
So
yeah.
for next week, right, we won't have any class on the Monday and Thursday on the
Oh
class
no,
time.
already lah. Monday we make it in the morning, 9:30 to 12 lor.
Then for the Thursday.
Thursday no more class lah, because I already spent more than 3 hours leh.
Oh, okay, sure.
Right? I just bring the, I mean, I cannot say today we just demo for 1.5 hours and wait for Thursday ma. So I lump it together. It's easier, right? So you also easy lah. You all finish everything. You all can relax, to do any other thing lah. Make good use of the Saturday, Sunday to get your thing run. So basically, I just want to get it done by Monday, okay, to wrap up this power electronics lah. So meaning power electronic evening no more class, and next Thursday also no more class because I have assigned schedule at 9:30 to 12:30, 9, 10, 11, 12, 4 hours. Like I say, the demo is roughly around 5 minutes. Okay, just make sure that yeah, you set up, run, start your MATLAB, Plex, everything, show me the demo. Okay, like I said, not necessarily all 3 of you in the group need to show me. Okay, you just need 1 or 2, depend because I know that some of the group, one is doing MATLAB, one is doing Plex, right? So each of you telling me which group you are. And then I know that even some of the group, one man do everything. I have no objection. You say, oh no, I do everything. The other, they just do nothing. They share the mark. I mean, don't come and complain to me because this is already your intention. And like I say, I do not allow 4 in the group. Okay, once I see 4, if I receive a report with 4 names, I will just divide it by 2. So that means the maximum mark is 15. So the chances for you to get low mark is very high. I won't say you will fail. Okay, and we have 115 students. So in my experience, most likely there are going to be many students going to get sub. So anyway, I already set 2 set of paper okay, to set sub there. So okay, they choose the paper by random. I'm not the one who choose the paper. Okay, easy or hard is really depend on how you perceive the question. To me, they are both equally same. For some students, they may think, which one is hard, which one is easy. This one only you can tell. So like I said, on the exam day itself, they will pick 1 set for you all. If you get it passed, then okay, congratulations, not to worry. And then for those who have sub, then you have to face the second paper. So yeah, but of course, I hope everybody pass so that I can save the time of marking the sub. But which I think is, yeah, when the class is more than 100, the chances of getting the sub is very, very, very high already. Okay. So, but anyway, yeah, that like I said, and one thing, right, for drawing, remember, for any drawing, okay, I'll ask you to illustrate this and that, right? Please draw it properly. Please draw it properly because I do appreciate drawing. And remember, as an engineering or engineer, drawing is one of your key skill you need to have. It's not you need to learn, it's you need to have, okay, for engineering. You cannot get away from drawing. Okay, try to draw it, okay, properly and nicely. I don't expect you to draw 100% correct, okay? Every dot, single point, but draw it in a nice and neat way. I still able to give you some marks for that, especially those in the borderline, like 25 or 24 over 50 lah. 1 mark only, the ruling thing. It can save you from this sub paper. So calculation is very straightforward. You have been doing calculation from year 1 until now, nothing much. Just show me the few steps. Don't show me the equation equals to answer. Okay. So some working step. Okay. The rest is drawing. Okay. So it's calculation and drawing. Okay. Basically, these are the 2 things only in my paper. Okay. Yeah. That's what I can say lah. Okay,
Sir?
yes.
For the drawing, only the circuit. We don't need to draw the MATLAB circuit, right?
No need. Only the circuit because you are not using MATLAB. So yes. Yeah, I mean, you can even draw like MATLAB. It's okay as long as the circuit is correct. Because it's going to be a physical exam. Okay, the key point, like I said, draw it nice and neat. Okay, and use the correct symbol. Okay. But nice and neat is the key, I would say. Sometimes you won't be able to really remember exactly or whatever, even I myself, right? Always, because nowadays we always refer. The most important thing is that you must know where to refer. And you must have the idea, oh, I saw this circuit before. Let's have a look at how this thing can solve problem. It's about solving problem. Like I said, yeah, exam system has its flaw, okay, but anyway, because we are living in this education exam system, anyway, we have to go through it lah. All right, yeah, any more questions?